Good afternoon, everybody. I will talk today about cold gas in giant elliptical galaxies and its role in galaxy evolution and in fueling radio mode AGN feedback. As you all probably know, black holes and galaxies seem to grow up together. Bigger the black hole, bigger the galaxy, bigger the supermassive black hole at its center. In this talk, I will focus on the high mass end of this relation, on the largest galaxies of the universe, which reside in the cores of galaxy clusters, groups of galaxies. These are giant elliptical galaxies. One good thing about these giant ellipticals is that they contain an atmosphere of hot X-ray emitting gas. Now, the cooling time of this hot atmosphere in the central regions of these galaxies is less than a gigayear. So if this gas would be unaffected by any heating, then this gas would just cool and eventually form stars. However, all of these galaxies also have accreting black holes producing very powerful jets. These jets are injecting relativistic plasma into this hot atmosphere, which forms bubbles. These bubbles initially expand supersonically and drive shocks, as we can see for this system here. And when these bubbles detach from the jets, they rise buoyantly in the atmospheres of these galaxies. And as they rise, they heat the gas, and they also uplift lower entropy gas from the center of these galaxies. So in this particular system, NGC 5813, which is part of our sample, we see actually several generations of bubbles. And from the work required by these bubbles, because these bubbles are, within these bubbles, to our knowledge, there is not much X-ray gas. These bubbles, as they expand, they push the X-ray gas out from this volume. And from the work required by these bubbles, we can actually calculate the jet powers. And here we can calculate how the jet power actually changes over time. So these systems are great laboratories to study the history of AGN activity and also test theories of formation and growth of massive galaxies, because all these processes, the cooling flows, AGN feedback, they must have been very important at high redshifts. All our galaxies appear red and dead. When we look at their optical images, we do not see much structure. We do not see any star formation in them. The stellar populations of these galaxies, of all of these galaxies, appear to be about 10 gigayears old. The most interesting, prettiest galaxy in our sample is NGC 7049, which has these beautiful dust lanes. However, the stellar populations of this galaxy are also as old as for these others. Many of the systems with hot X-ray emitting atmospheres display really spectacular network web of H-alpha filaments. This galaxy NGC 5044 is particularly pretty. It has filaments going out to distances of 10 kiloparsec from the core of the galaxy. But these H-alpha filaments are not associated with any star formation. So here, the ionization mechanism and the heating mechanism which heats this 10,000 Kelvin gas that shines in H-alpha is not star formation, it's something else. And what it is part of the thing that we want to solve here. Also, in these systems we see AGN. Are these AGN powered by only accreting hot gas or also cold gas? Steve Allen in 2006 found this beautiful correlation between the jet power and the accretion rate from the hot X-ray emitting phase onto the black holes. This correlation indicates that most of the time it is hot gas being accreted onto the black hole. But is there perhaps also an underlying correlation between accreting cold and hot gas phases? This is a question that we would like to know an answer to. So to search for cold gas, truly cold gas in these galaxies, and to study its properties, we used the Herschel Space Observatory, and we looked at cooling lines of C2, O1, and O1b. C2 was our primary probe. C2 is an excellent tracer of cold 100 Kelvin gas. It's an excellent tracer also because its flux is several thousand times stronger than the CO flux in galaxies. So we also imaged all of our galaxies with the SOAR telescope in H alpha plus N2. I already showed you NGC 5044. There are other beautiful systems which have spectacular filaments, which seem to be interacting with the radio bubbles. And we have two systems which have disky morphologies in H alpha. So in every single galaxy which has extended H alpha nebulae, we detected C2 gas. And we detected really booming C2 line, very strong. In 4 out of 9 systems, we also detected O1 lines, and about half of the systems also the O1b line. And with Herschel, we were able to also map the spatial distribution of this cold 100 Kelvin gas. And in each case, it is tracing the H alpha nebulae. So the H alpha emitting gas seems to be just a thin skin on an underlying reservoir of cold gas. And that's true for all of the systems with extended H alpha nebulae. The good thing with Herschel, we could also measure the velocities. And in systems which are filamentary morphology, at first the velocity distribution seems more chaotic because these filaments are interacting with the radio bubbles from the AGN. But interestingly, when you look at the velocity distribution, it's always the same when you look at H alpha or near infrared or which traces 1000 Kelvin gas and C2. In 2 of our systems, we see actually that the cold gas forms rotating disks. The velocity dispersions are between about 100 kilometers per second to 250 kilometers per second. These are the velocity distribution of the many small filaments with small volume filling fractions along our line of sight. This is not the velocity dispersion within the particular filaments. So, interestingly, we found a beautiful correlation in the systems with extended H alpha nebulae between the H alpha luminosity and the C2 luminosity. We see that the C2 over H alpha ratios are very similar in the range of 0.5 to 0.8 in all of these systems, which indicate that the C2 and the H alpha have the same heating and ionizing source. There are 2 outliers from this, and these are these 2 systems which have no extended H alpha nebulae. The filaments are also dusty. The systems which do not have extended H alpha nebulae have only 24 micron emission, so only dust associated with stellar mass loss, but no true interstellar dust. These other systems have lots of dust, lots of interstellar dust. So all these filaments are dusty. And there is no correlation between the jet power and cold gas. So if you have more cold gas, you do not have stronger jet powers. Quite the opposite. Actually, the 2 systems in our sample which do not have cold gas have the highest jet powers. So one particular filament in M87 we studied in lots of detail. And what I want to show you here, that the H alpha filaments, which are also cospatial with the C2 emitting cold gas, they are also cospatial with 10 to the 5 Kelvin UV emitting gas, and also with soft X-ray emission. this is a narrow band 0.7 to 0.9 keV soft X-ray image, and you see this beautiful correlation between soft X-rays and H-alpha emission. There is an association, this shows it perhaps better. This is 0.5 keV X-ray gas, which is associated with these H-alpha filaments. The hotter 1 keV gas, here the correlation is not that great, but you still see that there is more 1 keV gas at these filaments. So it looks like cooling from the X-ray phase at the very first sight. In all of these other galaxies, we also see that the H-alpha filaments really trace the lowest entropy X-ray emitting gas in all of the cases. So what is their structure, and what did we learn about them? The filaments actually consist of many strands with very small volume filling factors. They, as I showed you, they contain multi-phase gas spanning a temperature range of at least 5 orders of magnitude, from down to 50 Kelvin to 10 to the 7 Kelvin. What we actually found in M87, and we see indications of the same in all the other galaxies, the thermal pressure of this 10 to the 4 Kelvin gas phase is lower than that of the surrounding ICM, which indicates the presence of additional turbulent and magnetic pressure support. So if the turbulence within these filaments is subsonic, then we need these filaments to have magnetic fields threaded by magnetic fields of 30 to 70 microgauss. So there actually could be significant magnetic pressure support within these filaments. And they also contain dust and polycyclic aromatic hydrocarbons, which is actually quite interesting, because what is their origin? Is it cooling, wet mergers, or stellar mass loss? The correlation with soft X-ray emitting filaments indicates that cooling from the hot phase would be the origin of this cold gas. But the presence of polycyclic aromatic hydrocarbons and dust indicates that points more towards stellar mass loss origin. So one question I actually would like to pose to theorists is it possible to form dust from just cooling X-ray? You have hot X-ray gas, you cool it, and then in the cold gas clouds, can you just by coagulation of atoms form dust? Is that possible? It would be, my instinct says no, and therefore I think that the likely origin of this cold gas is cooling from the X-rays, and then this cold gas is being enriched by dust and by additional cold gas by stellar mass loss. And within these cold gas clouds, there is not much sputtering, which would normally destroy the dust if it would be just outside of these cold gas clouds. Okay, I have just 2 minutes, so I will just continue. All the galaxies which contain lots of cold gas look very disturbed. These are pressure maps, X-ray pressure maps. Look, for example, at NGC 5813. This is that galaxy with lots of bubbles. This is the pressure. You see that the low pressure areas are areas where you have bubbles of relativistic plasma, which provide the additional non-thermal pressure. All these filaments are on the sides of these bubbles. They are interacting with these bubbles. Here is a shock front. These filaments are behind this shock front. So all these galaxies which contain cold gas have very strong radial mode AGN activity, which indicates that intermittent accretion of clouds of cold gas onto the central AGN triggers outbursts, depositing the energy at small radii. On the other hand, the systems with no cold gas look very relaxed in X-rays. These are the pressure maps. It looks very, very regular. However, these systems have large radio jets. Even though they look so regular, they have large radio jets with large powers, depositing their energy at these larger radii. which indicates that the systems with no cold gas are accreting from the hot X-ray emitting phase at a very steady rate. So in the future, I actually would like to follow up on this. Now we detected there's C2, so we know that there must be CO emission, and with ALMA we will see it very easily. And I would like to map the CO emission close to the black holes at radii of 7 to 15 parsecs. We will be able to access this direct vicinity of the black holes. And this is my summary. Thank you.
Actually, I was just trying to look this up, but perhaps you did the exercise already. So at the X-ray temperature and typical densities of your cluster, what is the dust destruction rate? Like, what's the time scale for the dust destruction?
It's actually, I cannot give you now a number, but it's very, very short. So
yeah, temperature is helpful, but the density is not as high. So I thought maybe there's still a loophole of giving you just 100 million years.
No, the dust is destroyed very quickly. So those two systems, which do not have cold gas, there the infrared emission is consistent with the steady state situation, whereas the dust is being produced, it is being steadily destroyed at the same rate as it is being produced. While those other systems have much more dust, so truly interstellar dust.
Just to follow up on this relationship between cold gas and morphology, if you actually look at the stellar distribution, stellar surface brightness, is there evidence for a disturbed morphology in the stars?
No.
Okay.
No.
So really not an indication that the disturbed morphology is a merger, for instance?
No.
Okay.
There is no indication for mergers in this system.